If you recall from the expansion joint lecture, there was some comment made on large rotation that Caesar 2 as a beam element model doesn't handle geometry in large rotation properly. And this will be a very short example that will exercise that point. We have a straight pipe from 10 to 20, straight pipe from 30 to 40, and a zero length expansion joint installed between 20 and 30. It has a bending stiffness of 1,000 inch-pounds per degree. Let's see how much rotation we get on that expansion joint as I put different forces at this end, and how much rotation and deflection we get when we put forces at the end. Here's my quick calculation. The bending moment at this point here, 2030, is some load times this moment arm. The moment at the point is equal, F equals kx, or moment equals bending stiffness times phi, the angle of rotation. So my angle of rotation is the force times the moment arm divided by the stiffness. Well, I told you that my stiffness was 1,000 inch-pounds per degree, and my moment arm is 10 feet or 120 inches. So my angle of rotation is straight math. That's exactly what Caesar 2 does. The load times 120 divided by 1,000, or 0.12 times that force, degrees. I'm going to use three different forces: 10 pounds, 100 pounds, 1,000 pounds. That means my rotation will be 1.2, 12, and 120 degrees. Does Caesar 2 give us that? Well, let's go back to a new model in Caesar 2 called geometry. Open up geometry. Look at the input. A rather simple model here. There's 10 to 20. Put the node numbers on it. 10 to 20. 20 and 30 are at the same point in space because the element 20 to 30, it has no length, but it's an expansion joint. There's my 1,000 inch-pounds per degree bending stiffness. So, what are my loads? I'll go out to the end of the system, and we see at node 40, there's F1 is minus 10, F2 is minus 100, and F3 is minus 1,000. What happens when we load the system? Do the error check, and that's fine. And let's look at our load cases. We don't want to wait alone, so let's delete that W, and I'll just drag and drop F1 there. I'll click on load case 1 and hit the plus sign twice. I'll put F2 as load case 2, and F3 as load case 3. I'm not interested in the stresses, I'll call them all sustained. What happens when I run these cases? Click the running man. It's complaining that I've not included the weight, but I'm going to say yes, keep on going. And here I am in the output processor. Now, I want to look at deflections. Let's do it graphically real quick. Look at the plot. Not that they are to scale. I'll look down the z-axis, and I will show deflected shape. There's the first one. This is F1. Here's F2. Here's F3. Now, again, these are not to scale, so they all show the same thing, but the pipe looks like it goes straight down. Let's look at the report for this. I'll look at the force 1 displacements. And what did I predict in my PowerPoint? On the first one, I was saying it should move down about 1.2 degrees. Back to Caesar 2, 1.2 degrees. There's my free end node. 30 to 40 is my last pipe, 1.2 degrees. Yeah, that's pretty good. It moves down 2.5 inches. Notice that it does not move in the X direction at all. It does not swing. There's nothing that makes the pipe move in the negative X direction. Again, we've got this beam sitting here, and it is not rotating. We're not building a linkage in Caesar 2. It's all built off that stiffness matrix. While we're here, let's quickly make a new report. I want to show in one report a displacement summary, similar to this restraint summary, but I wanted to carry the X displacement, Y displacement, and Z rotation for these three load cases. How do you do that? I'll use this toolbar here. I wish to add my own custom report. On this machine, there's one called test 1, 2, 3. I'm going to build a new one. I'll make this quick. The title will be called DISPL Summary. That's going to be the name of the report, Displacement Summary. It is not an individual report, it is a summary report. And I said I wanted displacements. Now the first column will be the node number. The first column that I will have control over will be whatever I put in here. I wish to have the X displacement. I will put that in my first column. precision is 2, that's fine. My second column will be Y. And my third column, like I said, was RZ. There, I made a report. I'll close this out. You want to save it? I say yes. Now, there's my displacement summary. So if I select all 3 load cases, it'll summarize them in one report. Do that report. So we're interested in node 40. No matter how much rotation I put on it, 1.2, 12, or 120 degrees, it doesn't move in the x direction, and it moves straight down. So here we have a beam, an element that is 120 inches long, and it moves down 250 inches. So that is not realistic. So when you get large rotation in your models, it's up to you to review this data to make sure it's not too large. These are very large. Even at 1 degree rotation is rather large for a piping system. And the mathematics works pretty good with those small rotations. But when you get large rotations, watch your numbers. So one final point on the PowerPoint, it kind of puts it together here. The stiffness path, in terms of vertical stiffness here, if I have a hot vessel here, directly linked to a cold vessel on this side, and this vessel gets hot, it moves straight up. The program, Seizure 2, will be missing this little bit of strain because Seizure 2 is not a geometric model, not a linkage model. It does not rotate. Now, there are special tricks you can use in Seizure 2 to make it follow this curved path, but typically this type of extra strain is missing from your analysis. We've run all the examples that were presented in the lecture. The one final closing point I want to make here, you can use Seizure 2 to locate, size, and evaluate a lot of different expansion joints. But this program capability does not substitute the knowledge and experience that is possessed by the vendor of that expansion joint. So I would encourage you to work directly with that vendor to select a joint and then evaluate the joint and make sure that it works properly in your piping system. So there you go, that's your expansion joints.